Okay, before continuing, we're going to go over a few things and then continue with the study guide. So here I've drawn a picture of a neuron, and we have the soma and dendrite and the axon. And the soma and dendrite, you can see there's the nuclei that I have drawn this circle and shaded it blue right here, right? And the axon, which is a protrusion that comes from the soma dendrites, and it extends all the way to the other end, and it ends at the axon terminals, which I have dotted in red on the ends. Now the axon terminals are of course part of the axon, they're just the end of the axon, so the terminal end of the axon. Now, an action potential will be initiated here, right at the beginning of the axon, and travel down the axon in this direction. Okay? And it will go until it reaches the axon terminals. Now, it should be noted that a neuron is a single cell, and this black outline is the cell membrane of this cell. It's just that the shape of the cell is very different than the shape of some other cells you've seen. For example, in a lot of central nervous system neurons, the soma and the dendrites are in the brain while the axon is extending into the spinal cord. And we'll see an example of that later. So the axon can be about 1 meter long, but the action potential is generated at the beginning of the axon and travels down the axon. Now we talked a little bit about the action potential, just giving you guys some sort of idea of what's going on. And if we look at just a little bit, a patch of membrane right here, okay? And we go ahead and take a close look at it. Here's my patch of membrane, the axonic membrane, and my cytosol is right here, right? And let's actually erase this now, just to get an idea. So we'll just write cytosol here, extracellular on this side, and extra on this side, right? Now, remembering that we still have the sodium-potassium pumps, we'll still have the potassium leak channels on all these membranes of the neuron, and that helps to maintain the resting potential of the membrane at minus 70 millivolts. And all those gradients that we talked about before are present. The sodium gradient, the potassium gradient, the calcium gradient, etc. So now what we're going to do is we're just going to look at one side of this membrane. Remember, this membrane is wrapping around in a cylindrical format, but just to make it a little bit easier for us to see what's happening, we're just going to look at it in this way. We're just going to remove this, and just look at this as a line. Remember, we are talking about a patch of membrane. We're actually talking about all the way around the cylinder, but we're just going to look at it in this way. And we said that, okay, if I were to look closely, as an action potential is traveling in this direction from the soma and dendrite side toward the axon terminals, if I look at like this part and then right next to it, what I'll see is if this is minus 70 millivolts, then this will be somewhere around plus 50 millivolts. And then they'll switch around, meaning that a little bit further, a millisecond later, what you'll have is plus 50 here, minus 70 here, and then a millisecond or so later, you have minus 70 here, and plus 50 millivolts here. These are all in millivolts, okay? I'm just not writing it in. So you have the switching of the membrane potential from resting potential to this depolarized state, okay? Now, that's all nice and dandy, but how does this happen? So we have depolarization, right? Here's my membrane, plus, 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 minus 70 millivolts. So we're just going to go with this thing that on the right is the extracellular, on the left is the cytosol. I'll write it up here, but from this point on, just sort of keep track of that. I'm not going to write it in every time, okay? And we go from that, process of depolarization is this, where it becomes positive inside and negative out, right? And you have membrane potential that is near sodium's equilibrium potential. We're going to say plus 50 for now and leave it at that, but somewhere around there. It'll be in the high positive numbers. And the process of repolarization is going from this depolarized membrane of plus 50 or so millivolts back to resting potential of minus 70 millivolts, okay? Now, we have only learned about two channels that are special. These two channels are only found on the axon membrane. And those are the voltage-gated sodium channels and voltage-gated potassium channels. Now, there are other types of voltage-gated sodium and potassium channels. The type that is on the axon membranes of neurons are special because they have these three states. Closed, is not conducting its ion. Open, it is conducting its ion. And inactive, where it's not conducting its ion. Okay? There are other voltage-gated sodium channels and potassium channels that exist that are not special in this sense. These are voltage-gated sodium and voltage-gated potassium channels on the axon that have some special properties, and one of them is that they have this inactive state that they go to after they open. Okay? And action potential is literally generated because of these channels closing and opening. So this whole process of depolarization and repolarization is being caused by the movement of positive charge. How is that so? So let's look at depolarization. Here's my membrane. Again, remembering the right is extracellular, the left is cytosol, and it's in resting state, where I'm positive outside and I'm negative in, minus 70 millivolts. Well, if I move positive charge in, I start making the inside more positive, and because I'm removing positive charge from the extracellular and moving into the intercellular, I'm making the extracellular negative, right? So this movement of positive charge in to the cell will lead to depolarizing the cell membrane, that patch of membrane. You just got to remember that it's just a patch, not the whole membrane. And you go to that plus 50, eventually to that plus 50 millivolt value that we're talking about. Now, repolarization, if I'm starting out from a depolarized membrane, where I'm positive inside, negative outside, and I'm at plus 50 millivolts, well, all I have to do is move positive charge in this direction, out. By moving positive charge out, what will happen is I'll become more negative inside, more positive outside, and I repolarize the membrane back to its resting potential. Eventually. Okay? How do we get this movement of positive charge? Let's look at what happens at rest. Here's my membrane again. It's at resting potential, positive outside, negative in. What is sodium's concentration across the membrane? So here's sodium. And we're about 145 millimolarity out and about 10 millimolarity in. What about potassium? Potassium is about the opposite, right? 5 millimolarity outside and 140 millimolarity inside. Now, we've done these calculations and you guys have answered questions on the quizzes and etc. about these gradients. And you know that sodium's electrochemical gradient is pointing strongly in. Because, first of all, the concentration gradient or chemical gradient for sodium is pointing in, and positive charge wants to go to negative, so its potential gradient is pointing in, and thus the electrochemical gradient is strongly pointing in. Now, for potassium, you know potassium is slightly pointing out, right? We've done the calculations, it's in the notes and the study guide. And this is, just to make sure, we're at minus 70 millivolts here, we're at resting. Now, what about a depolarized membrane, where I'm positive in, negative out, and I'm at 50 millivolts, plus 50 millivolts, right? Well, those gradients are still the same. So let's just write out the gradients. Sodium, 145 millimolarity, about 10 millimolarity. Potassium, 5 millimolarity, 140 millimolarity. Now, sodium's gradient is somewhat gone. Okay, at 50 millivolts, you guys have done the calculations to figure out what the equilibrium potential for sodium is at these concentrations, and it's around this number, 50 millivolts. So we'll just say sodium is sort of near equilibrium. So we sort of put a double arrow saying that it's near equilibrium at this potential. But now let's look at potassium. Well, potassium, its concentration gradient is pointing out, but now so is its potential gradient. So when you add it up, you have a strong electrochemical gradient pointing out, okay? When the membrane is depolarized. So if I want to go through the process of depolarizing a membrane, here's my membrane. It's at rest at -70, positive outside, negative in. If I make the membrane permeable to sodium, sodium will rush in. And that is the equivalent of positive charge rushing in. And this will lead to depolarization, where you become positive in and negative out. Right? By just making the membrane permeable to sodium, sodium will come in. And that's the equivalent of letting positive charge in. Now, if I am in this depolarized state, positive inside, negative outside, and I make the membrane permeable to potassium, what will happen is potassium will leave the cell, or this patch of membrane, and positive charge is leaving, and this will lead to repolarization of the membrane back to a negative value. Because I'm making the outside more positive, and by default, since positive charge is leaving the inside, it makes the inside negative. Now I go from plus 50 millivolts back to resting potential eventually. Okay? Now, another way to sort of look at this and to appreciate it is that the membrane potential will get pulled toward the equilibrium potential of whatever it is most permeable to. So let's take a look at that website that we were using before. Here's the website, and we're going to go down to the calculator, and we're going to fill with sample data, and we're going to put in outside 5, and I think we have 145 here. This is all good. We'll put 10 for here. I think we had 140 for CL. And then 10 is fine. And we're going to say calculate. We wanted in millivolts. Calculate again. So about -70. Now, if I scroll up a little bit, you can see that right here we have VK, VNA, VCL. And these are the equilibrium potentials that are calculated the way you guys learn how to calculate it. So you can see for potassium is actually near -90. For sodium is 71.43, and Cl- is -70.5. Now, the membrane, if you look at the PK, PNA, and PCl values, which are the permeability values for these different ions, the bigger the number, the more permeable the membrane is. The membrane at rest, because it has those potassium leak channels, is most permeable to potassium, and it's pretty permeable to Cl- too. So the membrane potential gets pulled down toward the equilibrium potentials for these two ions. It's slightly raised because the membrane is slightly permeable also to sodium, and sodium has this big positive equilibrium potential. Now, if I were to make the membrane very permeable to sodium, much more permeable than it is, even if it's just for an instance of time, so we'll go ahead and increase it to 50 and hit calculate, you can see that now it's moved towards sodium's equilibrium potential, which is 71.43, and now we're at 62.17. It's not going to completely reach sodium's equilibrium potential because the potential on the membrane is still being pulled down slightly because it is still permeable to potassium because of the leak channels, and it's still permeable to Cl-, right? So now if I go back and reset this to what it was before, we go back to resting potential, and I make the membrane very permeable to potassium, much more than it already was by 100-fold, then you can see I get pulled down immediately to potassium's equilibrium potential of near minus 90 millivolts. The membrane's potential will get pulled towards the equilibrium potential of whatever ion it is most permeable to. And what these voltage-gated potassium and sodium channels are doing are they're making the membrane very permeable for an instance of time, a very small, short instance of time, like a millisecond, just a patch, just a small patch, to that ion, therefore changing the potential on that membrane for a short period of time. Alright, so let's go back. Alright, so we're going to look at repolarization, going from a depolarized state, or positive in, negative out, and we're at plus 50 millivolts, near sodium's equilibrium potential. So at plus 50, it's very permeable to sodium, right? So the membrane potential is pulled towards sodium's equilibrium potential, which we saw was plus 70 or something, right? And this is the state of depolarization, meaning that the membrane is depolarized. Now, if I make the membrane permeable to potassium, and it goes back to the initial permeability value of sodium, meaning that those voltage-gated sodium channels now have gone to the inactive state. They're no longer conducting their ion, but now I have opened up potassium channels, those voltage-gated potassium channels. What will happen is the membrane will become hyperpolarized. They become very positive out and very negative in, and the membrane potential moves towards potassium's equilibrium potential, which is around minus 90 millivolts. So in this state, permeable to potassium, and the membrane is said to be hyperpolarized. Okay? Now, what will happen next is that both of those voltage-gated potassium and sodium channels are going to be in a state where they do not conduct ion anymore. So the permeability of the membrane goes back to the resting state permeability, which is that it's more permeable to potassium, but not at the levels that it was before. So you go back to this. Because you've gone back to the normal permeability of the membrane to sodium, potassium, and Cl-, well, the membrane potential returns to the resting potential of minus 70 millivolts, right? The resting potential. So resting permeability at this point. Okay? And this is, the resting permeability is just because the potassium leak channels are always open. The membrane is slightly permeable to potassium, and it's slightly permeable to Cl-. So if we're going to go back to that web page and talk about exactly what's happening, so I go ahead and make the membrane very permeable to sodium, right? So here we go. We're going to go ahead and make it very permeable to sodium. And okay, I'm near 62 millivolts plus 62, so the membrane is depolarized. So now sodium's permeability goes back to baseline, but potassium's permeability increases, let's say by 10-fold, 100-fold, and we go to minus 90, right? Now we're in hyperpolarized state. And now we go back to the permeability state of the membrane, the resting permeability state of the membrane, and we go back to the resting potential of the membrane, which is near minus 70 millivolts. Okay guys, I hope this clears up some questions that you might have had. And if you can understand what we just talked about here in this video, you're going to have a very easy time understanding everything else that's coming up. I recommend writing everything that I just presented, writing it out, thinking about it a bit, and trying to recreate it yourself. And that will help when we start talking about the action potential and everything else dealing with the neuron from this point on to the end of section 2. Okay? Alright guys, I'll talk to you later. Bye-bye.